Please let me know if we are back up. Okay, so I stopped the the stream and restarted. Okay. All right, good. Sorry about that, guys. So unfortunately, this is going to be a two-parter for the video. Sorry about that. So did you hear, are you good with all those? I said I was just going to start with the equation because I've already solved the problem many times. Of course, if I ask you to do this, you would need to solve for this equation first, then you can use it. Now, I was saying that we have two conditions there, two initial values, or this is an initial value and then a boundary value. We want to use the one that's 0 first, and we have to do that because we have only one equation and two unknowns, c and k. So to get rid of those, right, we have to, or to solve for them, we have to get rid of 1. So to do that, if I plug in t equals 0, then this term goes to 1. So 300 is equal to 70 plus c1 e to the k times 0. This term right here goes to 1. And so we get 230 by moving this over here is equal to c1. So then we can rewrite the equation again. This is now temperature equals 70 plus 230 e to the kt. So I see someone said I have no idea what's going on. Okay, how far back did we lose you? What happened on the second line? Right here, I plugged in this value. So big T was 300, and I plugged in little t is 0. Sorry, I see that let me move over because I see I'm in the glare there. So we do that again. I'm plugging in for the temperature. Yeah, I got it. 300 is equal to 70 plus C1 e to the k, and I'm plugging in 0 for little t. Okay. So k times 0 is 0. That means this exponential here goes to 1. If I move this over, that makes that 230 equals C1. And then over here, this is just a equals T. Couldn't see that before. Okay. So this is our constant. Once we take that and plug it back into the equation, we now have temperature equals 70 plus 230 e to the kt. So we've solved for c now. We just need to find k. We can use our other value that was given. So now the temperature is 200. That equals 70 plus 230 e to the k, and little t is 3. So let me just step out here for a second, make sure you guys can see it. Alright, so to solve this, I'm going to move this 70 the other side. That's 130 equals 230 e to the 3k. I'm going to divide by 230. That equals e to the 3k. Get rid of the zeros, no need for them. The only way to get rid of that exponential e is to take the natural log of both sides. So this is natural log of 13 over 23 is equal to, and if I take the natural log of e, it disappears. So I get 3k. That leaves me with k equals 1/3 natural log 13 over 23. Let me go ahead and calculate that really quick. So I'm going to truncate it there at negative 0.1902. This is one of the few cases where I'm okay if you go ahead and plug in a decimal and use a decimal. So the last thing we can do then is write the temperature equation again. And so the temperature is now 70 plus 230 e to the minus 0.1902 times little t. That is the equation for the temperature at any time t. So the last part of the problem asked, when is it okay to eat? Well, I guess that kind of depends on how hungry you are. Right? It's kind of a vague question, so if I were to give you this on a test, I'd be more specific. I'd say maybe when does the cake get down to 100 degrees Fahrenheit? So to solve that, you would just set big T to 100 and then solve the equation for little t. So how about I give you guys 2 minutes or so to solve that part of the problem. If anyone has questions, you may pose those during that time. And if not, go ahead and try to solve for little t here when the temperature is 100, and then someone go ahead and put their answer up on the chat for me. Yes, Jimmy, I said solve for when the temperature big T is 100. All right, do you want an approximate? Yes, there is an approximation because we've got one we've already made here, so that's fine. So I saw one answer. Does anybody agree or disagree with that? All right, so we got a couple 10.7, so that's good. All right, fantastic. All right, so any questions about this problem? Okay, so some people are saying they're good. So I'm going to go ahead and erase. I'm going to go ahead and then go to the next problem. The last problem gave us this equation, right? To start the problem, I solved the equation, which was this guy. So you would need to do this each time you were given a Newton's law of cooling problem, at least for the test. All right, when you're done with Calc 2 and you're working as a CSI guy, then you can do whatever you want, but you would need to solve for that equation, then use the values. But because I've already solved for them and you guys can go back and look at it and I'll give you the notes, I'm just going to go ahead and start here again and finish this next problem. So let me just erase this. So while I'm doing that, how do you guys feel about this so far? Besides obviously the fact that we got dropped there for a second. Yes, I am putting them on YouTube. Yes, I'd rather be in class as well. So forgive me for being naive. Can somebody explain to me what the little caret's for when you're doing your chat? Pointing to the last message. Gotcha. So basically just agreeing. Guys make me feel old. All right. So let's look at the next one here. My mouse wants to work. Or not. Come on, mouse. Oh, I'm on the wrong screen. That would explain it. Hey. There we go. All right. So yes, I agree. I would much rather be doing this face-to-face. But unfortunately, these circumstances do not allow for it. So just do the best that we can. And like I said, if you guys have suggestions or things that you would like me to do, go ahead and put them in the chat. Send me emails. Quizzes. I haven't decided on what to do with the quiz exactly yet. I may do the same format, or I might just give them to you as like a take-home thing. So like I have some time today. I'll try to make up a quiz, send it to you, and say, get it back to me by the end of the night. Or I may possibly do like I said I was going to do with the tests and just put it up here on the screen and say, okay, 20 minutes, write an answer, send it to me. I will decide on that in a little while. All right. So this is a problem. It says thermometer is taken from inside a room to the outside. and outside the temperature is 5 degrees. So that's telling us that T sub m is 5. After 1 minute, the thermometer reads 55. So that tells me T of 1 equals 55. After 5 minutes, it reads 30. So T of 5 equals 30. What is the initial temperature of the room? Okay, so again, I've already solved for the equation, so I'm just going to start with it. We know that it's T equals Tm plus C1 e to the kt. I have Tm. I can plug that in. I need to solve for C and K. However, notice this time I do not have a 0 for little t. So I have one equation, two unknowns, and no way to eliminate one of the unknowns. So I'm going to go ahead and just plug in both of these in separately and see what it looks like. So first off, T sub m we know is 5. So I'm going to plug in this first condition. It says that 55 must equal 5 plus CE to the K times 1. Okay. Then I'm going to plug in little t equals 5 and big T equals 30. So 30 equals 5 plus CE to the K times 5. I can simplify these slightly by moving this 5 on both of them to the other side. So I now have 50 equals CE to the K, right? I don't need to write the 1. Yes, the equation we solve for applies to any law of cooling problem. However, when I ask you to do it, you have to solve for that equation. Okay, and then this one here would be 25 CE to the 5K. Any thoughts on how I might be able to solve this? It is a system of equations. So would you like to use substitution, elimination, or something else? So for this one, okay, so I agree that it's an elimination. It's just not in the sense that we're used to. I'm going to divide both of these equations. So by doing that, these C's can cancel. And now I've got 2 is equal to e to the k divided by e to the 5k. And if I have that division, well then the division here I can just do as a subtraction of the powers. So this is e to the k minus 5k, which is e to the minus 4k. So now I've got 2 equals e to the minus 4k. If I want to get k, I need to take the natural log of both sides. That will cancel with the e. And so it's pretty easy to get k from there. K is equal to minus 1/4 natural log of 2. So again, let's get an approximation for that. So to 4 decimal places, I got negative 0.1734, or sorry, 33, let's say. So once I have k, I can plug it back in, and I can use either of the 2 conditions to find c. So right now, I have that the temperature is equal to 5 plus C1E to the negative 0.1733 T. But I still need C, so I'm going to use this condition. So it says that 55 equals 5 plus C1E to the minus 0.1733 times 1. Again, we can easily bring this 5 over. So 50 equals C1E to the minus 0.1733. And finally, C1 is 50 divided by e to the minus 0.1733. So for that, I got 59.46 approximately. So if I take that and plug it back in here, my final equation looks like that. Any questions about that guy? Now it does ask us one more part. It says, what is the initial temperature of the room? So to solve that, I would just need to let little t equals 0. So big T would equal 5 plus this 59.46 e to the negative 0.1733 times 0. That's going to go to 1. And so my temperature turns out to be 64.46 approximately. Alright, so if you guys are okay with that, I'm going to go ahead and erase that problem. And as I'm doing it, please feel free to ask any questions. I'm going to go ahead and pull up sequences in series, and we'll just briefly start that. And then, as I said, next time we'll go ahead and do a review, and I will give you the exam next week. See if dual erasers can get the job done. Whew. Pretty sure that was the last problem on the packet. Let me just check. Yeah, looks good. Okay. So close that. You may see a picture of me with Stan Lee for a second. If it actually closes. Yep, there we go. Right. I can see the chat going crazy, but I can't read it because I'm doing stuff. Right. Let's get the chat back up. I lost it. Okay. Yes, I did. I got to meet Stanley. And I joked that he was a wax statue when I met him. You weren't informed about what earlier? Oh, well, that's not exactly an important topic. All right. So, sequences. A sequence, by definition, is a list of numbers with a pattern. And we can talk about sequences as though they either converge, which means they equal some constant, or they diverge, which means that they approach some infinite value. So the first exercises here say plot the first 10 corresponding values of each sequence, then determine if the sequence is convergent or divergent. So if you all have your calculators or don't have them, please go grab them now. I'm going to go ahead and plot this on Mathematica while you're doing so, and then I will talk you through how to do it on your calculator. All right, so our sequence was -1 to the n times 2 to the n divided by n factorial. Great, so let me just drag this onto the screen. So there's Mr. Wolfram. That is our sequence right there. Someone having some difficulties again? All right, if you guys don't mind, we'll just give them a minute here. What did that say, Mr. Doctor what? Mr. Doctor, how do... Come on, chat. Being rude. How do you use factorial on the calculator? Jimmy, I'm going to tell you that right now. All right. So, in your calculator, first, go to Mode. The fourth option down, you should see Func for function. Go to the fourth option to the right. It says SEQ, that's sequence. And I would like you to hit enter. So then to exit this, you're going to hit second and hit mode again. That'll bring you back to your main screen. Then go to y equals. Put in the function, so -1 to the n. You'll notice that you now see a u sub n, or a un. Let me see if I can get this on the screen for you. I don't know if I have enough light. Okay, you see we have u of n now. So under that, you're going to type in the function, so -1 to the n, 2 to the n, and then divided by, and I will tell you how to get to n factorial. So you're going to put n, and by the way, n is just the same thing as the x key that you normally use. It just now puts in n because you're in sequence mode. So to get factorial, you're going to go to the math key, third down on the left. Go all the way over to PRB, that's probability. And it is your fourth option. So you can hit 4, or you can scroll down and hit enter. I would suggest making your zoom standard and then plotting. Anybody, if anyone's having trouble with their calculator, you know I have office hours basically right after this session. So if you like, we can do a Zoom meeting and we can talk face to face and I can show you how to do it. So I cut my window down so that I have only positive values of x because there can't be negatives here. And I don't know if you can see those little dots or not. Probably not with all the shadows. Maybe you can see them there. So that is just the same plot as we have here, done on Mathematica. All right, no problem, Will. If you have time, just set up a Zoom account after class, and I'll be happy to show you how to do it. We can do a multiple session, so if there are other people that are having trouble, we can all get in and do it there. So this is my plot on Mathematica. So you see, this is what we would call an alternating sequence, which we're going to call an alternating series very soon. The points change sign, so the first one's negative, then it's positive, negative, positive, and you see that they're getting closer and closer together. So we would say that this sequence is converging, right? All the points are headed towards a single value. And in this case, that value is 0. So you'd be asked to draw this picture. Where's my mouse? There we go. And then we would write here, converges. To 0. All right, so what I'll do is after the session, I will set up a meeting and I'll just email you guys the link. So if you want to be a part of that, just let me know. So far I got Clem and Will. Any questions about this guy? All right, Brentley, got you. Frank. Well, so far it looks like we're just going to have to do the whole class. Does that sound right? All right, so there, sorry, what's this? Do you want us to draw out the sequence? Yes, I would ask you to plot the first couple terms and then tell me if it converges or diverges. So that's why we plotted on our calculator. Can you put the calc direction on Blackboard? Sure, I can do that. All right. So any questions about why that converges? So I said they were lost from the beginning. So let me do this next one and see if it helps. I'm assuming you're saying the calculator portion. So this is another sequence. It's almost the exact sequence we just had, except now instead of 2n over n factorial, we have the opposite. We have n factorial over 2n. So if I bring back Mr. Mathematica, I'm just going to cheat slightly here and just say that this whole section Where'd the other parenthesis go? Is to the -1. That'll flip it over effectively. And I rerun it. Notice now I get this as the plot of my sequence. So the points start out really close together, and then they start spreading apart. This last point is too big to be on the screen, I believe. They didn't make the scale big enough. So we would say that this guy then is diverging, because the points are not heading towards some value, they're separating. So yes, you guys are right, it is diverging. So again, you would just give me this plot and you would say diverging. So those are sequences. They are quite simple, except for the calculator code maybe to put them in. And the whole point of learning sequences is that we eventually have to do series, and we'll get to that in just a second, or we may have to leave that for next time. We'll see. So we've just looked at a sequence and its limit graphically. We can now do that analytically. And to do that, we can simply find its limit. So if we take the limit as n gets really big or heads towards infinity of the sequence, and it equals some value, right? So here it says L. If L exists, meaning L is some number like 5 or -1,000,000, then that thing converges. If L does not exist, meaning some negative infinity or positive infinity, then it diverges. So now all we have to do is take the limit of these sequences as n approaches infinity. So you may remember this from Calc 1. So the first one here is, and let me just change this. I keep forgetting to do it. This is silly to have 1 plus 7 down here. Make this a 7n. So I want to take the limit as n approaches infinity, 3n squared over 1 minus 5n squared plus 7n. Now these are infinite limits. If you recall, in Calc 1, there is a special little thing you may remember. It says that the limit as x approaches infinity, 1 over x to any number r equals 0. But this is only for r greater than 0. Now we're going to need that fact to be able to solve the limit that we're looking at. Now I don't know how much you remember from Calc 1, but in order to solve this type of limit, it's easiest to divide by the highest power of n in the denominator. So I'm going to divide every single term by n squared. And when doing that, it will simplify. So I divided everything by n squared here. They'll cancel there. I'll leave this alone. This becomes minus 5. This becomes 7 over n. Notice my 3 looks a little odd there. Let me fix it, at least from my view. There we go. All right. So now if I evaluate the limits, anything that's got n in the denominator as n goes to infinity, as long as n is to a positive power, will go to 0. So these two terms go to 0. And I'm left with minus 3/5. So we can say that this sequence converges to minus 3/5. I'm going to go ahead and start the next one. If you have any questions about this one, feel free to ask. All right, so down here, let's just bring this guy over. Again, I need to use the highest power in the denominator. So first let's write limit as n approaches infinity. And this is the, oh, wait, sorry. So the numbers over n are 0. Yes, anything that's 1 over n or 7 over n or n squared, when I take this limit, those values become 0, because 1 divided by infinity, right, is really small numbers, which goes to 0. And same thing for 7 over n. Can we just look at the leading terms? You can, in most cases. It's not exactly let me think about that. So yeah, you could certainly use those things when you're talking about asymptotes, which is basically what we're doing. But when you say, can we just look at the leading terms, I don't want you to just, at the beginning of the problem, just go, oh, well, there's my answer. Right, I would like to see some calculus done to show me how you got there. Certainly check yourself that way. All right, so limit as n approaches infinity. I've got the square root 4 plus 2n to the 4th, all divide by 5n squared minus 6n. So every one of these guys, I'm going to divide by n squared. However, if I put n squared inside the radical, recall, n squared is a result of taking the square root of n to the 4th. So if I put n squared in the radical, it becomes n to the 4th. So when I come over here, this is limit n approaches infinity. This becomes square root 4 divided by n to the 4th plus 2n to the 4th over n to the 4th, all divide by, now on the outside, I am dividing by n squared. So this is divided by n squared, and this is n squared. So I'm going to pause here because I'm assuming there's going to be a question about this. Anybody confused with what I just did? Okay. So the n squareds cancel there. One of the n's there. N to the 4th's there. I am left with limit n approaches infinity. I have the square root 4 over n to the 4th plus 2 all over 5 minus 6 over n. So again, I use the fact that if the thing is going to infinity, 1 over x, or in our case n, to any positive power must go to 0. Therefore, this term and this term go to 0. Left behind is a constant that has no bearing on the limit, and so I have square root of 2 over 5. So if you guys are okay with that, I'm going to go ahead and erase those. The other thing that I wish that we could do is I can no longer have you guys working at the whiteboards. And I could give you time to try problems on your own, but I know that at least in my other classes, some people had some restrictions with their internet and so forth. So if that's something you guys would like to try, you have to let me know. I wish that I could have you reply directly, like put your work up here. I have heard people say use Discord, but I tried doing that over the break and I had a little bit of trouble. I couldn't quite figure out how to use the video portion. Talking about the glare. That light is actually from the projector. So I don't know if you could tell, but the projector is sending this image up to the board. And that's how I'm overlaying it on my dry erase board here. And I had to put the camera over there to try and reduce that glare. Alright, so let me go ahead and finish up these problems, and then, like I said, if you guys are interested in doing some of the work on your own, then maybe we can try that the next time that we have class. Alright, so this one I want to take the limit. I wrote limit out completely, but I did. As n goes to infinity, natural log of n squared over n. So if I tried to plug in infinity right now, I get infinity over infinity roughly. That should tell you use L'Hopital's rule. And so L'Hopital's rule, if you remember, says take derivative of the top and the bottom. I'm going to be a little bit clever before I do that. This square is on the n, which means I can go ahead and throw it down there. Then take the derivative of the top, which is 1 over n, and there's a 2 there. and derivative of the bottom is 1. So this is just limit as n approaches infinity, 2 over n. And so this is, if we direct substitute, 0. So this also converges, which I realize I haven't written for the last two, but I should have, and this one converges to 0. So I think I have one more example using L'Hopital's rule. I'll just leave that there for a second in case you guys are copying or have questions. What did the last two do? So 2 meaning the number 2, I'm assuming. So here I'm guessing is what you're referring to. And so you're dividing by big numbers. I don't care if this is 500 or 5,000, right? Or 2 dividing by infinity is going to go to 0. So yes, whatever you get out of the limit, it converges as long as this is some number, and it converges to that number. All right, so this is another example here. I would take the limit as n approaches infinity of n squared e to the minus n. If I can think of one, yes you can. I don't have one that actually diverges, but it would just equal infinity. So I can make one really easily. We could just say something like limit n approaches infinity of n squared. Right, that's a perfectly good sequence. You just have all the squares, so 1 squared, 2 squared, 3 squared, so on. If I take the limit as n goes to infinity, this goes to infinity, that diverges. So here I have one. If I try to direct substitute, this would be infinity, and e to the minus infinity is really 0. And if you don't like that, then think of this. Right, this is really 1 over e to the infinity. Yes, you can also graph them, but we are currently doing it analytically. So you would be asked to do both. So for instance, I might give you a problem that says, here's a sequence, plot the first 10 terms, prove that it or tell me what it diverges or converges. If it converges to a number, give me the number, and then prove analytically whether it converges or diverges. So this is one of the, I don't like to call them indeterminate forms necessarily. I like to leave that term for infinity over infinity, 0 over 0, that sort of thing. But it is one that says you can use L'Hopital's rule, you just don't have it in the right format yet. So I need to take this e to the minus n and put it in the denominator. And when I do that, it becomes e to the n. And if I were to try to direct substitute now, I would get infinity over infinity. And that is a clear indeterminate form that L'Hopital's rule can be used. That means I can take derivative of top and bottom and apply the limit again. So this is going to be 2n over e to the n. You plug in. You once again get infinity over infinity. So I have to take another derivative. So limit n approaches infinity. This becomes 2 over e to the n. If I plug in there, I get 2 over infinity, and oh again, I get 0. So this one converges to 0. I don't remember if there are any other sequences here. Let me just look. Nope, we start series. So any questions about that problem before I get into series? All right, thank you. So it seems like most people are good. So I'm going to go ahead and erase this and start some series. And if we're lucky, I can get you guys done a few minutes early. So as I said, the whole point of learning sequences was because we want to talk about series. So we have infinite series, which we're going to get into. But first, what is a series? Well, the definition of a series is nothing more than the sum of the terms in a sequence. So just a minute ago I said we could use the sequence n squared. Well, here's the same thing. It's just written as I. So this is the sequence of I squared, which is 1 squared, 2 squared, 3 squared. But it's a series because it's the sum, right? This is sigma, if you're unfamiliar with that, and that means sum of those terms. So 1 squared plus 2 squared plus 3 squared. And we only do the first 3 here because this sum runs from 1 to 3. So we plug in 1, 2, 3. The second example there runs from 5 to 9. So you'd plug in 5, 6, 7, 8, and 9. This one, however, is what I was alluding to earlier. It's alternating. So when you plug in 5 here for k, you get a negative 1. But when you plug in 6, you get a positive 1. And then every odd becomes negative, and all the evens are positive. So this is alternating terms, alternating signs, right? One of them's plus, then the next one's minus, or vice versa. So those are finite series, right? They run over some small range of values. But we can also have infinite series. And an infinite series runs from typically 1 or 0 to infinity. So you can write it this way. If it runs from 1 to infinity, you can kind of cheat a little bit and just write the sigma notation. And just like before, where we had that sequences could converge and diverge, we also have that series can converge and diverge. Where's my mouse? So to converge, we just need the infinite series to equal some value L, and L is just some real number, so something tangible. The series diverges if it goes to plus or minus infinity. So basically the same set of rules as the sequences. And a little note here is that there are many series that are convergent, but the value of L to which it converges either cannot be found or is not important. So we are going to do, I think, a total of 3 series, infinite series, where we can actually find the sum. All of the others, we don't care. So keep that in mind. So I think with the time we have left, I'm going to do a couple of these geometric series, and then we'll have to pick up there when we get back to this stuff. So let me just introduce the concept and maybe do 2 of them. Then I'll leave the rest of time for any comments and questions you guys might have. So what is a geometric series? It is a series of the form a times r to the n. You could just as easily write this a out in front, because if you look, every single term here is multiplied by a. So it has no bearing necessarily on the inside of the summation. We can find the sum of a geometric series. Now note, this is starting at 0. So if we prove that it converges, which requires this r, which you can basically think of as a ratio, if the absolute value of that r is less than 1, we can say it converges, and the sum, if it starts at 0, is equal to this. If it does not start at 0, say instead it starts at 1, then the sum is a times r over 1 minus r. Okay, so all the ones in the packet are previously written starting at 1. I'm going to change a few of them as we go, just so you can decide when to use which one of these. So, geometric series converges if absolute value of r is less than 1, and it diverges if absolute value of r is greater than 1. Can I explain which part again? I'm assuming the summations. Okay, so if the sum starts at 0 and it converges, which means that the absolute value of r is less than 1, the sum is equal to this value. If it starts at 1 instead, if n is 1 to begin with, your sum is a times r over 1 minus r. So let me do a few, just these first 2, and I'll do one of each and see if that makes sense to you. So the real trick here is just getting these into the correct format. So this first one is 2 times 3/5 to the n minus 1. Well, I don't need something to the n minus 1, I need something to the n. So how in the world do I do that? Well, if I have something to a power, I can split it up. So I can rewrite this as 3/5 to the n times 3/5 to the -1. And then this 3/5 to the -1, that's really just 5/3. And so I can combine this 2 and 5/3 here and make it 10/3. So this is now in the proper form. I have some a, some constant, times some ratio r to the power n. So this is a, that's r. Now in order to prove that it converges, I need to show that the absolute value of r is less than 1. Well, r is 3/5. So is the absolute value of 3/5 less than 1? Absolutely it is. So therefore, this converges. And if it converges, I can go ahead and find the sum. So I need to go back and say, okay, my sum started at 1, my summation. And so the total overall summation, the sum, for 0 is this, for 1 is this. So I started at 1, I need this formula. So my sum is 10/3, that's A. R is 3/5 over 1 minus R, which is 3/5. So then we can simplify. These 3's can go. 10 over 5 is 2. 1 minus 3/5, that's 2/5. This is 2 times 5/2, which results in just 5. All right, so in the equation, AR over 1 minus R, does n equal 1, so n can be any number. If you were to write out the entire sum, which you could never do because it's infinite, you would start at n equal 1 and then plug in 2, 3, 4, 5, 6, and go on forever. So in that case, right, using the terminology that way, n can be any number. For these types of series, yes, n can start at any number. I am only going to give you ones that start at 0 or 1, which means you only need that formula or that formula for the summation. If you went farther, I believe you just write this r to the power. So r to the 0, r to the 1, the next one. So if it's n equal 2, it's r to the 2nd. But let me check on that formula. Or if you get a chance, look that up. But you don't have to do that. I'm just going to ask you for starting at 0 or starting at 1. So we proved that this geometric series converges, and it converges to a summation of 5. Any other questions about this guy? Couldn't we have also used an integral? what later on we're going to use an integral test to see if something converges or diverges. Technically, because this is a summation and it's an infinite one, I suppose the integral would work, although that would be somewhat of a interesting integral, I believe. You don't often integrate constants to a power x. Not that it can't be done, it's just not something that you're often taught to do. Alright, so I'm going to do one more for you, and then like I said, I'll leave the last 10 minutes or so for you guys to make any comments, ask any questions. We can get that conference call set up so we can look at the calculator stuff. Alright, so this last one right here says the sum n so I'm going to change, let's go ahead and change this to n equals 0. So n equals 0 to infinity, 1 over square root of 2 to the n. So again, I'm trying to get it into this form. This one's a little interesting because I can take the fact that 1 to any power gives back 1, which means I can just do this. You can always email me if you don't have time right after class about the calculator or any other questions. Alright, so as I said, 1 can be written, right, 1 is equal to 1 to the n basically, because n, as long as n is, well, any value n here gives you back 1, so we can rewrite 1 to the n instead, so it means I can jump right to here, which means this guy is my r, and my a is just a 1. Right? There's nothing out there besides a 1. So a is 1, r is 1 over the square root of 2. I need to find out if it converges. So is the absolute value of 1 over square root of 2 less than 1? Square root of 2 is 1.4, so 1 divided by that is going to give you something smaller than 1. So yes, it converges. And if it converges, we can find its sum. I started at 0 here, which means I can use that formula for my sum. So the sum is 1 over 1 minus 1 over root 2. If I multiply every single term there by root 2, it would become that. Either one's acceptable, this one's fine. All right, so we proved that this converges, and then we found its sum starting at 0. So I'm going to go ahead and stop the recording for today. I'll leave the stream up here for another 8 minutes. If you guys have more questions, feel free at the end of 8 minutes. I will email you guys about the Zoom meeting. So thanks for getting up and putting on your happy faces, which I can't see. Hopefully this wasn't too bad for you. And if I don't talk to you guys, enjoy the rest of your day.